We're going to start with the basic ideas of induced current and Faraday's law. So basically, we'll start off with what Faraday's experiment was, how he actually showed that you could use magnetism to create electricity, or changing magnetic fields to create electricity. And what he realized, that if you moved a wire through a magnetic field, so even a wire that had no current going through it, a current would be driven through that wire, just because the kind of the reversed motion. So the moving electric charges had a force on them, and then if you forced them to move, there would be you push them through, there would be a force acting on them. And this is really the basis of all modern power generation, other than solar panels. All of it comes from Faraday's experiment, his idea. So basically what happened when you move the wires, a voltage, we're going to use the symbol as script E for EMF. They called it the electromotive force, which isn't exactly right. It's actually a voltage, not a force, so be careful with that. And the faster you moved it, the greater the current, and the current would go through wires that weren't connected to a battery. Right? It just has to be in some kind of circuit to make the net charge balance. All right, and then to explain that, he came up with the idea of magnetic flux. Anytime I mention this, people start thinking of flux capacitors, or at least those people who are the type of people who think of Back to the Future. But flux just means flow, and the symbol for that is the Greek letter phi, and basically an I with kind of with an O on top of it. It's the amount of flux going through something is the magnetic field times the area, how much area perpendicular is going through. So it has to go, it's how much of the flow actually, goes through that area. And usually you can have electric flux or magnetic flux or any kind of flow through an area. So we'll use the magnetic flux, and it'll be a cosine theta, and we'll talk a little bit about where that cosine comes from. Usually we're going to ignore it. All right, now one way to do this, I'll have an experiment set up where we'll have a current meter, an ammeter, and then a solenoid, and then if you bring a magnet, which has this magnetic field, into the solenoid, what happens, nature really is kind of lazy, and what happens is anything, kind of the inertia of the situation, opposes change. So if we move this magnet here, it's going to try and increase the flux to the right. So to do that, to oppose that, there will be an induced current in the opposite direction, to create a magnetic field in the opposite direction. All right, it's not going to be enough, because there is some resistance. It's not going to be enough to completely cancel it out, but it will reduce it. And that's kind of where you get this current from. So the EMF is always set up so there's a new magnetic field in the opposite direction of whatever's changing. We'll look at how that works on Wednesday. So the EMF is equal to negative, so that's the opposite direction, times n, this is the number of loops, times the change in flux in the time interval, how fast you're changing this flux. So what happens, you're going to get an induced field in the opposite direction. So the magnet tries to move in, you get a magnetic field the opposite way. Then if you move the magnet back out, the magnetic field induced will be in the opposite direction. Current will be in the opposite direction. And the same thing with the south pole, it'll just be negative. So you'll be able to see that in class, the actual effect of moving these magnets. All right, then we can actually get that same effect by doing what's called motional EMF, moving objects related to a magnetic field. So a couple of variables here. It's going to be moving along. We'll call this distance along here x. So as this moves, the amount of area of this loop is going to change, because this wire has a length L, side x, and it's moving along there. So we're losing energy. So basically, the flux, because we have one loop, is going to be along there, so the absolute value of it is going to be BL, and the change in x over the change in time, but the change in x over change in time is just the velocity. So the EMF generated when we have a wire moving through a loop, or moving across some rails there, is basically the basis of any electrically driven situation. So everything from a rail gun that the Navy uses to an electric train. It's magnetic field times the length of the wire times how fast it's going. So that's the voltage. And so the current is just voltage divided by resistance, so it's BLV divided by R. So those two main equations, the idea for the sometimes it's called the motional EMF versus just the generic equation for Faraday's equation, delta phi over delta t, are the two main equations we're going to need. And the way this works is when you're actually generating electricity, what happens, you have a loop of wire inside a magnetic field. And so as that spins around, you're either doing that by spinning a turbine, by burning natural gas or coal or something like that. As it's moving along, it spins, and what happens is the direction of the current is going to oscillate. And so what happens when you get power out of the wall, because this is the way electric current is generated, this is the way the voltage is supplied. It's going up and down 60 times every second. Right? And this is all just a direct result of Faraday's law. All right. Well, I hope you have a good middle of the week, and I'll see you guys on Wednesday.